Netflix streams to over 200 million users worldwide. Imagine trying to ensure a consistent viewing experience while dealing with unreliable networks across the globe. This is the challenge of distributed systems, where the CAP theorem reigns supreme. Here's what most engineers overlook. It's not about times avoiding times network partitions, it's about times how you handle times them. By the end of this video, you'll understand how to navigate the trade-offs between consistency, availability, and partition tolerance, and make the right choices for your system. We'll cover the CAP theorem and its extension, PayCalc. Remember that 200 million user number. We'll see why that scale matters when we discuss availability.
Let's break down the CAP theorem. First, consistency. Every read receives the most recent write or an error. Imagine a bank account. After a deposit, everyone should see the updated balance immediately. Next, availability. Every request receives a non-error response, without a guarantee it contains the most recent write. Think of a social media feed. You might not see every time's new post instantly, but the site is always up. Finally, partition tolerance. The system continues to operate despite arbitrary message loss or failure of part of the system. This is critical because network partitions are inevitable in distributed systems. The CAP theorem states that you can only choose two of these three guarantees at any given time. You can't have all three simultaneously. The reason is that during a network partition, you must choose between consistency and availability. Stop. Think about this. Which is more important for your application? Building on that foundation, let's dive into how these trade-offs play out. Network partitions occur when communication between nodes in a distributed system is interrupted. Now, let's consider CP systems. These prioritize consistency and partition tolerance. If a partition occurs, the system might refuse writes on one side to maintain consistency on the other. Think of a financial system where data accuracy is paramount. They might use a two-phase commit protocol to ensure consistency across all nodes. Then there are AP systems. These prioritize availability and partition tolerance. During a partition, both sides continue to operate, potentially leading to inconsistent data. Social media platforms often fall into this category. They might use techniques like vector clocks to track causality and resolve conflicts later. Finally, CA systems. These prioritize consistency and availability, but they cannot tolerate network partitions. In reality, CA is more of a theoretical construct, as partitions are unavoidable in distributed systems. The key insight is that when a partition occurs, a choice must be made. Sacrifice availability to maintain consistency, or sacrifice consistency to maintain availability. There is no third option. Here's the twist. What happens if the network partition lasts for hours?
This brings us to a crucial challenge. How do real-world systems navigate these trade-offs? Consider a social media platform like Twitter. They often choose AP, prioritizing availability so users can always post and view content, even if there are temporary inconsistencies in the timeline. This often involves eventual consistency. Eventual consistency means that if no new updates are made to a data item, eventually all accesses to that item will return the last updated value. It's like gossip. It spreads, but not instantly. To manage this, they often employ base properties, basically available, soft state, eventually consistent. This contrasts with ACID properties in traditional databases. Now, imagine an e-commerce platform's inventory system like Amazon. They might choose CP, ensuring that inventory counts are always accurate, even if it means temporarily slowing down or restricting sales during a network partition. The reason is that overselling an item is far more costly than a temporary slowdown. The trade-off decision depends heavily on the specific business requirements and the cost of inconsistency versus unavailability. Remember the 200 million users from Netflix? High availability is crucial to avoid impacting that massive user base.
That said, there's a hidden problem here. The CAP theorem is often oversimplified. This is where the PayCalc theorem comes in. PayCalc states, if there is a partition, P, how to choose between availability, A, and consistency, C. Else, E, if there isn't a partition, how to choose between latency, L, and consistency, C. This means that even when the system is operating normally, there's a trade-off between latency and consistency. A system might choose to sacrifice some latency for stronger consistency, or vice versa. For example, a system might use synchronous replication for strong consistency, but this increases latency. Alternatives include asynchronous replication, which reduces latency but weakens consistency. The reason is that synchronous replication requires all nodes to acknowledge the write before it's considered complete, while asynchronous replication allows the write to be acknowledged immediately, with replication happening in the background. The pros and cons of each approach depend on the specific requirements of the system. The key takeaway is that trade-offs are always present, even in the absence of network partitions. So, what are the key takeaways? The CAP theorem forces you to make trade-offs between consistency, availability, and partition tolerance. The Payselt theorem extends this, highlighting the latency-consistency trade-off even without partitions. There's no one-size-fits-all solution. The best choice depends on your specific use case and business requirements. As a cheat sheet, consider a 2x2 matrix, high availability versus strong consistency. In the top left, AP systems like social media. Top right, CP systems like banking. Bottom left, systems that are neither highly available nor strongly consistent, rare. Bottom right, CA systems, theoretical. Now, go forth and build resilient, scalable systems armed with the knowledge to make informed trade-offs. If you found this helpful, like and subscribe for more deep dives into system design.
Want to master more engineering concepts and coding patterns? Subscribe for weekly tutorials that answer the questions developers face in real interviews and projects.